Now we're going to talk about expressing vectors in the other two representations, magnitude angle representation and component representation. So first I want to talk about components and what that means, and then we'll get some practice going back and forth between magnitude angle representation and component representation. And in this video you'll see why we were practicing trigonometry at the beginning of this semester, because you need to use all your trigonometry skills for this. So the components of a vector are the projections of a vector along coordinate axes. What does that mean? Let's draw a picture. So let's say we have a vector A, looks like that, and I place it on a coordinate system with an x-axis and a y-axis. Now the idea of a projection is like if you imagine that you shine a light from up here, it would cause the vector to cast a shadow along the x-axis. And the length of that shadow is the x component of vector A. Similarly, you could imagine a light bulb over here shining a light on vector A. It would cast a shadow on the y-axis, and the length of that shadow would be the y component of vector A. Now, you might notice this looks an awful lot like right triangle trigonometry. And it sure is. Because if we know this angle, then we can express those two components in terms of the hypotenuse or length of that vector and the angle. So I'll just draw this as a right triangle now instead. There's the hypotenuse with A, the length of the vector. By the way, when we label a vector, we write the symbol with an arrow on top. If we get rid of the arrow, that just means the length or the magnitude of that vector. So I'm using A without an arrow to indicate this is the length of the hypotenuse. So here's AX, here's AY, there's the angle, and if you remember your trigonometry, SOHCAHTOA, AX is A cosine theta, AY is A sine theta. So this is how you find the components of a vector if you know its magnitude and angle. And of course, Pythagorean theorem tells you that the hypotenuse is the sum of the two sides squared. And trigonometry tells you that this angle is the inverse tangent of AY over AX, opposite over adjacent. So these are just the properties of right triangles, now using our new vocabulary where we're calling these two sides the components of vector A, and we're calling the hypotenuse the length of vector A. So this is all trigonometry that you've done before. We're just using new words. We're using components for the legs. We're using length of the vector or magnitude of the vector for the hypotenuse. All right, so now we can talk about those three representations of a vector. We've already learned about graphical representation. That's where you draw a picture. So this is the graphical representation of vector A, just that arrow. The second representation is the magnitude angle representation. Where you specify vector A as having a magnitude or length. I use those two words interchangeably, magnitude and length. They mean the same thing. So vector A has length or magnitude A and an angle theta. And the third representation is the component form. Component form where we say vector A equals an ordered pair, the x component, comma, y component. Or you can write it like this. AX times this thing we call a unit vector, that's a letter I with a little caret or hat on top, plus AY times J hat. So either notation is okay. Both those notations are saying vector A has this value of x component, that value of y component. And you can go back and forth between these two representations by using your knowledge of trigonometry. So we should do an example calculation here to see how this works. Let's say vector A is given in magnitude angle form. So A is represented by 5 meters in length and an angle of 20 degrees above the positive x axis. So we're given the vector in magnitude angle form. Let's represent the vector in graphical form and component form. So what is A in graphical form and component? Well, graphical is pretty simple. You just draw a picture. Five meters and 20 degrees, so 20 degrees is maybe like that. So there's vector A. In picture form, in graphical form. Now let's find the components of vector A. So we can think of vector A as being the hypotenuse of a right triangle, where we've got two sides, AX and AY. There's the right angle. And trigonometry says that AX will be 5 meters times cosine of 20 degrees, because that's the adjacent angle. Adjacent is cosine. And that's 4.7 meters. AY, that's the side of the triangle opposite to the 20-degree angle, so it gets sine 1.71 meters. So in component form, vector A equals 4.7 meters, comma 1.71 meters. Or if you prefer, you can write it as 4.7 meters I hat plus 1.71 meters J hat. I know that second notation looks weird. It's just another way of saying the component along the x direction is 4.7 meters long. The component along the y direction is 1.71 meters long. People use these two notations probably about equally. Okay, let me do some more examples. Next example, I'm going to give you the vector in component form, and we'll express it in graphical form and magnitude angle form. So let's say this vector, I'll give it a different name this time, just so you don't get in the habit of calling everything A. We'll call this one V for velocity. And I'll give it units of velocity. So let's say we have a velocity vector in component form represented by minus 2.5 meters per second in the x direction and 1.75 meters per second in the y direction. So let's express this in graphical form and in magnitude angle form. Again, graphical form is pretty easy. You draw a picture. All right, my tick marks aren't so evenly spaced, but that's okay. So when you're given the components of a vector, you can just plot it like you're plotting a point, and then connect the origin to that point. So we go minus 2.5 along x and 1.75 along y. Sorry my points are drawn so poorly, but it would be somewhere around there. So there's my V vector. All right, we did it in graphical form. Check. Now, magnitude angle form. when you're dealing with vectors that aren't in the first quadrant, I think it's helpful to just picture them as a right triangle. Just by itself. So here's our right triangle. And then, once you've figured out the values, go back to your graph and figure out the angle you need. Because you can get in trouble using your calculator to do inverse tangents, because your calculator doesn't know the difference between like the second quadrant and the fourth quadrant, and the first quadrant and the third quadrant. So let's just take our vector, turn it into a right triangle with no coordinate system. We'll figure out this angle and then put it back in the context of our graphical representation. Okay, so there's our vector as a right triangle. We know from Pythagorean theorem that the length is square root vx squared plus vy squared. We have minus 2.5 and 1.75. That gives you 3.05. It's still a speed, still has those units in meters per second. And this angle is the inverse tangent of opposite over adjacent opposite Vy, adjacent Vx. And so here's what I'm talking about. This is 1.75. This length is 2.5 meters per second. So we'll just do 1.75 over 2.5, forgetting about this minus sign, because we're just looking at it purely as a triangle. That gives you an angle of 35 degrees right here, which means that this angle is 180 minus 35. And generally that's a safer way to do this, because if you start putting minus signs into inverse tangent calculations, half the time you're going to be wrong by 180 degrees. So just draw a picture of the triangle, label the lengths of each side, those lengths will be positive, and find the angle in your picture, this angle 35 degrees right here, and then you can measure this angle with respect to the x-axis if you want. Or you could say this vector is 35 degrees above the minus x-axis. Whenever you express an angle, whenever you write down an angle, it's good practice to let the reader know where you're measuring it from. If you're measuring it from the positive x-axis over here, or if you're measuring it from the negative x-axis, just let people know where that angle is measured from. Okay, so we've done this problem now. We have V given to us in component form. We expressed it in graphical form by drawing a picture, And we've now also expressed it in magnitude angle form. By finding its length, 3.05 meters per second, and finding that angle, whether you want to call it 35 degrees above negative x or 145 above positive x, either way is okay for expressing the angle. Now I want to make one more comment about this example in particular, where we started out with a velocity. This is a velocity vector. It has a direction. Whether you express it in component form or magnitude angle form or graphical form, it's pointing in a certain direction. Notice when you calculate the magnitude or the length of that velocity vector, you get the speed. The speed is the magnitude of the velocity vector. It's the thing you get in that magnitude angle form. Okay, now I'm going to do one more example where you're going to see how to add vectors together numerically using component form, and it's super easy. Let's say you want to add vector A plus vector B. We know how to do it graphically. You draw a picture where you connect the start of B to the end of A. You can't do this in magnitude angle form. There's not really a good way of doing it. You need to express your vectors in component form, and once you do that, adding them is really straightforward. That sum is ax plus bx, comma, ay plus by. The x components add together, the y components add together. So for example, let's say vector A equals 1, 2 in component form. Vector B equals 3, 4 in component form. Then A plus B equals 1 plus 3, 2 plus 4, which is 4, 6. Super easy to do. You could also, if you expressed your vectors like 1 I hat plus 2 j hat and 3 I hat plus 4 j hat, then the sum would be 1 plus 3 I hat plus 2 plus 4 j hat like that. That's the way you'd write it using this other notation in component form. So if you want to add vectors together, get them in component form. If you're given vectors in magnitude angle form, you need to convert them using your trigonometry skills into component form, and then you can add them together easily.